So we've talked a lot about what happens to a sample when you transfer heat to it, um, both in temperature change or state change. But we should talk a little bit about heat transfer mechanisms, right? How is heat transferred? Um, so there are three main ways we're going to talk about. The first one is conduction, which is just heat transfer through a material from atom to atom, right? So atom to atom transfer would be like you put a spoon in, say, a cup of hot tea, right? And so there's your cup of hot tea. How do I know it's hot tea? Sure, it's red. Red is hot, right? Actually, we'll talk about why we think about red as hot. So there's my cup. And what color is the spoon? I don't know. Do I have a silver? Fabulous. So here's my spoon. That's great. So if you wait a little while, you'll feel that the end of the spoon is warm, right? It takes some time though, right? Well, how much time? That depends on the rate of heat transfer. That's what we're talking about, is rate of heat transfer. Which is basically a power, right? Rate of heat transfer here, we'll call it Q over delta T. Again, that's energy per unit time. So the unit here is a joule per second, or a watt, as we've seen in the past. So heat transfer rate for a solid object, so this is conduction through an object, depends on how long that object is, how thick that object is, and what that object is, right? So you can imagine the heat transfer rate through a metal spoon might be higher than the heat transfer rate through a plastic spoon or a wooden spoon. And so we model this. We say K times, let's see, so K is our thermal conductivity. We'll get back to that in a second. So the heat transfer rate should depend on how long this thing is. The longer it is, the slower this rate should be. So the heat transfer rate should probably be indirectly or inversely proportional to length. It's directly proportional to area. This is a cross-sectional area, right? So a thicker spoon can transfer heat faster than a thinner spoon. Think of it like a bottleneck, right? If there is no bottleneck, the cross-sectional area will be bigger. If there is, A will be smaller and the power transfer rate is smaller. And then a delta T. Oops. Which just means the temperature difference between the ends of the spoon. So if the spoon is already if the entire spoon is at the temperature of this T, there is no heat transfer because there's no driving force for it, right? So the driving force for this heat transfer is a temperature gradient, a temperature difference. So that delta T would be the temperature difference between the ends of the rod. And again, that K, this K is the thermal conductivity. And thermal conductivity depends on what the material is. So let's look. I have a list of some thermal conductivities in the lecture handout. So here, metals have thermal conductivities that are tens to hundreds of joules per second, joules per second meter degrees Celsius. Again, that's just the unit that comes out of setting joules per second equal to K times a length times a delta T times an area times a delta T divided by a length. All right, we can go through that if you want some other time. Okay, so metals have relatively high thermal conductivities, as you might expect. Non-metals, we've got wood. Wood there's 0.08 as compared to, let's say you have a silver spoon, right? Silver spoon is 400. That's quite a bit bigger, right? That actually tracks. That makes a lot of sense. Water has a fairly low thermal conductivity. Ice has a higher thermal conductivity. That kind of makes sense. Air has a very, very small thermal conductivity, right? Air is actually a great thermal insulator. Okay, that's great. So let's go back then. Let's do an example while we're here. Let's do an example. So here I have a silver rod with a length of 83 centimeters and a cross-sectional area of, a diameter of 2.4 centimeters, and we're going to conduct heat from a reservoir at a temperature of 540 degrees to an otherwise completely thermally insulated chamber that contains 1.43 kilograms of ice. Where in your life would you see an example like this? Now, this is completely constructed for a physics example. That's okay, though. That's okay. Not every example can be a real life example. So let's talk about this for a second. Reservoir. What do I mean by that? A reservoir is generally a large body. It's intended that you can take heat away from it and add heat to it and not change its temperature significantly. It'd be like saying, pour a cup of boiling water into Lake Michigan. How does the temperature of Lake Michigan change? It doesn't, right? You have technically increased the thermal energy of that body, but not by enough to change its temperature because it's just very large. So that's the idea here is I can take heat away from this end of the silver rod and not change the temperature. So that's like T hot. That's like one side of this is 540 degrees. And the other side is ice, right? That's like T cold. The ice is sitting at 0 degrees Celsius, and I want to melt the ice exactly. So here's the beautiful thing of this problem. As you melt the ice, its temperature doesn't change. So delta T here is 540 Celsius the entire time. Right? So delta T, not that T, delta T is 540 degrees Celsius. Right? Or really Celsius degrees. Since it's a relative, not an absolute temperature. If that were not the case, if this were, how long does it take to heat up some water from 15 to 25 degrees? You would have to use calculus because the rate would be constantly changing. All right, but that's not the case we're in, luckily. Or you could do it stepwise, right? You could do it 1 degree at a time and assume it's constant over that, but that would be like a step toward calculus. That's how you build integration, actually. Okay, so let's gather the rest of this information. What else do I have? A length. The length of this rod is 83 centimeters, so let's convert it as we go. That's 0.83 meters. And we have a diameter. So the diameter of this rod is 2.4 centimeters. So 2.4 times 10 to the minus 2 meters. And the question is, how long does it take to melt this ice? 1.43 kilograms of ice. The question is, what is delta little t? Okay, well, so our rate, our equation is Q over delta t equals K A over L times delta big T. Right? So I've got a length, I've got a delta temperature. This is silver, so I can look up K. Right? Let's move this out of the way just a little bit. This is silver, so K was like 400, right? K is 420. I think it might have been not quite exactly that, but let's go with 420 to 2 sig figs. And again, that's joules per second meter degree Celsius. And from that diameter, I can figure out an area. We'll plug it in. No, we'll just solve it right now. Let's use a different code. So from this, we can say area is pi r squared, or pi fourths d squared. This is the same as saying pi d halves squared, since radius is half the diameter. This is a common trick for me, so I don't have to divide the diameter by 2. I just divide the whole thing by 4. Diameter is easier to measure generally, so that's why diameter is often what's given. Okay, so we can do this math. I think what you get is 4.52 times 10 to the minus 4 square meters. Okay, we are honing in on the answer. The only other thing we need now is Q. How much heat do I need to transfer to melt 1.43 kilograms of ice? Well, that's a previous idea. Let's do this in another color. Let's do that color, whatever color that is. So Q is M times the heat of fusion. Right? We've seen this in the past. So that's 1.43 kilograms. And the heat of fusion for water is 3.33 times 10 to the minus 6. Nope. 3.33 times 10 to the 5. Positive 5. That's joules per kilogram. So you do that math and you get 476,000 joules. And I'm going to keep more digits just to keep from rounding before the final answer, so we can avoid some rounding error. Okay, so we're so close. We're so close. So now we can just plug all this into this equation, right? So I get 476,190 joules divided by delta time equals K. That's 420 joules per second meter degree Celsius times that cross-sectional area, which was no, that's right. Cross-sectional area goes upstairs. 4.52 times 10 to the minus 4 square meters divided by length, which is 0.83 meters. 83 meters. Times that delta T, which is 540 Celsius degrees. And if you do this math, you can solve for the time, and what you get is 38:52 seconds. Or pretty close to an hour. I think it's 64 minutes. Cool. Great. Okay, so let's ask another question. Because this was only one mechanism for heat transfer. But the second, go back. The second mechanism for heat transfer I want to talk about is, what if instead of going through a material, you transfer heat by actually moving the hot material? Think about an oven, right? So how does an oven work? Well, there's a coil, an electric coil, and that heats up the air, and then the air transfers heat to the baked good, right? But we just said air is a terrible conductor of heat, and actually has a pretty low heat capacity. So if you've ever heard of a convection oven, convection is another way to transfer heat. Convection is just again, motion of the hot thing. So that would be like imagine a warm front coming through, right? So you just replace the cold air with warm air, and that's much more efficient than transferring heat through the air. Same way that an air conditioner works, right? Instead of trying to change the temperature of the air in the room, replace the air in the room with different temperature air, right? And then suck air from another place that's at the wrong temperature, take it to somewhere like you through your furnace or through the air conditioner, change its temperature there. That works well for air because air is easy to move because it's light and it's fluid. Okay, so that's great. Let's talk about one other mechanism here. Let me draw. Ooh, what I need is here. Let me draw this. So this is intended to be a campfire. That's the beginning of a campfire. What else goes into a campfire? I don't know, like that's great. And then maybe some orange. And we'll call it good. Maybe a brighter orange. That's okay. And then some yellow. Great. There's my campfire. And I built it too close to the previous part. Sweet. So let's say you're standing next to the campfire. And in fact, you're warming yourself next to the fire. Oh no. I wanted another arm. There. You're happy. How are you getting warm from the campfire? How is the fire transferring heat to you? Well, it's certainly heating up the air, but it's not heating you through the air via conduction, right? Because we just said air doesn't conduct heat very well, and you can warm up from a fire, like a campfire or a fireplace, pretty efficiently. And certainly, if you stood over the fire, hot air would physically move to you, so that would be convection in that case. But you don't want to stand over the fire, and you don't want to heat your house with air coming from the fire because that would be laden with smoke and carbon dioxide and carbon monoxide. That's bad. That's why you have a chimney. So, what is heating you? Well, the answer is radiation. What do we use? Let's use, I don't know. That's great. Whatever color this is. Radiation. Radiation is light. And we'll talk about that in much more detail in the next course. But radiation is another means for heat transfer. In fact, if you think about the sun, the main way we get energy from the sun is through radiation, right? There's nothing in space, so there's nothing to conduct heat from the sun. And the sun does eject some mass, and we do get like solar wind from the sun, but that's not how we get the majority of the energy from the sun. What we generally get is light, right? So we can write the power that we get from the sun in an expression that Maxwell Planck helped us come up with. Not Maxwell Planck. Max Planck. Maxwell is another guy. So the power emitted, so we could say Q over delta T, the power emitted by a hot object is E sigma A T to the fourth. So let's talk about those things. E is the emissivity of the surface, and that has to do with how well that surface absorbs and emits light. All right, so this is different for different things. It's different for metals than it is for cloth, than it is for wood. Um, you can imagine, like when you take a black shirt or a white shirt into the sun, the black shirt absorbs more light, so it has a higher emissivity, and the white shirt reflects more light, so it has a lower emissivity. So emissivity is generally a number between 0 and 1. This sigma here is the Stefan-Boltzmann constant. Sigma is the Stefan-Boltzmann constant. It's just a number. It's 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. Area here is surface area. And T is temperature. But it has to be in Kelvin because it's absolute temperature, not relative temperature. So let's do a quick example. So the surface temperature of the sun is 5,800 Kelvin. Let's estimate the rate at which the sun radiates heat into space, assuming that the emissivity of the sun is 1. That's a pretty good estimate for the emissivity of the sun, because we're basically asking how much of the light that hits the sun reflects off of it. And compared to the light that the sun is emitting, right? So the sun emits light, that light reflects off of things in the solar system, and then goes back to the sun. Most of what we see from the sun is actually sourced at the sun and not just reflecting off of the sun. Okay. So what are we given? The temperature is that, and that's a surface temperature. I can make it better, okay. The emissivity is 1. The radius of the sun is 6.96 times 10 to the 8 meters. And the question is, how much energy, at what rate, right? At what rate is it sending energy into space? So that's Q over delta T. Okay, so we're just plugging in. So Q over delta T equals E sigma A T to the fourth. So we're told the emissivity is 1. Sigma, again, is 5.67 times 10 to the minus 8. You see that? 5678. Not that you have to memorize it, but again, meter squared Kelvin to the fourth times the area. So I need the surface area of a sphere. It's actually 4 pi r squared. So there's a 4 pi. R is 6.96 times 10 to the 8 meters squared. I ran out of space. Is there any way to fix that? There is. Fabulous. Times temperature to the fourth. That's 5,800 Kelvin to the fourth. And if you do this math, you end up with 3.9 times 10 to the 26 watts. As expected, the sun is dumping an enormous amount of energy into space. And in fact, the surface temperature of the sun was estimated using this idea. So it's actually backwards. The sun emits light, and the earth receives some of it, right? So we have a sense of how much, like what fraction of the total we're getting, and we can backtrack to this number and then use this expression to figure out the temperature of the surface of the sun. That's how we know the temperature of the surface of the sun. Isn't that interesting? Okay, so here are 3 ways that energy can be transferred. Conduction, convection, and radiation.